A very happy day to all. So today we have to see the concept from computer system architecture. The subject code for that computer system architecture is 7BCA5C2. So in computer system architecture we have see the third unit. So from third unit I have see some concept. So what are the concept means? Today I have to cover what is central processing unit, next general register organization, at the last we have to see stock organization. First we have to see central processing unit. So all of them know about CPU. So already we know which is the main component of the computer. So it is the brain of the computer. CPU means central processing unit, which is the brain of the computer. So here we see that what is the component are in CPU and how they connected with each other. So that general architecture of CPU we will see. So in CPU means which is the part of computer that performs the bulk of data processing operation is called central processing unit. So the commonly it's referred as CPU. So the major parts of CPU is register set, control unit, ALU. So register set is nothing but which is a small storage element. So small storage element and also fast accessible. So control unit, which is nothing but so that controls all other components in CPU. Whole components are controlled by this control unit. At the last ALU means arithmetic logic unit. All the arithmetic and also logical part of the calculations are done in the ALU unit. So this is the major components of CPU and how they communicated are shown in this diagram. So the control unit monitors the register set and also the arithmetic logic unit. So both arithmetic and logic unit and register set are connected with each other through the bus, through the common bus. So bus is nothing but which is a set of wires. So set of wires are called as bus. So through that wires we have communicate with each and every parts of the CPU. So the bus may be a data bus or address bus. A data bus means the data are transferred through the database. Address bus means the address of the data are transferred through the address bus. So both register set and also arithmetic logic unit are controlled by this control unit. So already I explained that register set, it stores intermediate data used during the execution of the instruction. ALU means the arithmetic logic unit which performs the required micro operations for executing the instructions. At the last, control unit which supervises the transfer of information among the registers and also instructs the ALU as to which operation to be performed. So next we have to see general register organization. How registers are organized in the CPU. So CPU have the large number of registers. So registers are the intermediate storage. So CPU contains so many registers and which are efficiently communicated through a common bus system. So already I said that what is bus? Bus is nothing but set of wires which is used to transfer the data or address. So the registers are communicated with each other not only for direct data transfer but also while performing various micro operations. Micro operations means nothing but the addition, subtraction, logical, shift. So these are all called as micro operations. So hence it is necessary to provide common unit that can perform all the arithmetic, logic and shift micro operations in the processor. So this is the diagram of general register organization and how the registers are communicated through the bus. In this example, here we specify 7 registers. So we know that registers are specified with the symbol R. So in this diagram, R1 to R7 are represented as the registers. So 7 registers are given here. So these registers lines are passed through the two multiplexers MUX A bus. So here we have used two buses for passing the value A bus and B bus. Those are passed the data into the arithmetic logic unit. So from these 7 registers we collect the input from only 2 registers. So that are chosen by this multiplexer because many to 1. So from 7 multiplexer we have given input from only from 7 registers we collect the input from only 1 register. So those are selected using select A through the with the help of multiplexer, and also as the same multiplexer to select B. So those data will be passed through the A bus and also the B bus. Those data are sent into the input of arithmetic logic unit. So which arithmetic logic unit performs the arithmetic or logical operations, and it will produce the output. So the output also stored in the 7 registers, one of the 7 register. So that which register we have to store the output, that will be chosen by the decoder 3x8 decoder. So which select the which register will be goes to store the output. So here we specify the control word. So control word is a nothing but which is a 14-bit word. So 3-bit for selecting selection A, 3-bit for selecting next B selection B. So 3-bit for destination. First 3 plus 3 stores the source. Next 3 bits stores the select the destination. And the last 5-bit specify which operation we have to perform those. Which operation we have to perform with these input data, and it will be stored in the selection T. So totally it have 14 bit. So in that diagram or display explained in this slide, so the output of each register is connected to 2 multiplexers to form the 2 buses A and B. The selection lines in each multiplexer select one register or the input data for the particular bus. The A and B buses from the inputs to a common arithmetic logic unit. The operation selected in the ALU determines the arithmetic or logic micro operation that is to be performed. So the result of the micro operation is available for output data and also goes into the inputs of all the registers. The output register is selected by the decoder. So the decoder activates one of the register to load inputs, thus providing a transfer path between data in the output bus and also the inputs of the selected destination register. Here I show one example. So here addition operation will be performed here. So R2, so input registers are R2 and R3. So it will perform the addition operation and the data are stored in the R1 registers. So R1 gives R2 plus R3. So selection A place the content of R2 into bus A. So next multiplexer B selector B to place the content of R3 into bus B. So the ALU operation selector to provide the arithmetic addition of A plus B. So which is the definition of control word. So control word is nothing but which is a binary word formed by the selection in the general register organization. There are 14 binary selection inputs in the control unit and their combined value specifies a control word. So this 14 binary selections combines the word specifies a control word. So first is 3 bits specifies the selection A bus. The next 3 bits specifies the selection B bus. Next bit 3 specifies the destination selection, and the last 5 bits specifies the operation, which operation we have to perform. Those are specified in this diagram. The 3 bits of selection A select a source register for the A input of the ALU. The 3 bits of selection B select a register for the B input of ALU. The 3 bits of selection T select a destination register using the decoder and its 7 load outputs. The last 5 bits of operation selected one of the operations in the ALU. So here I give some examples of ALU operations, encoding of ALU operations. The binary code triple bit 0 specify none. So input will not given. Output also not be given. So next 1 specifies the register 1. 10 specifies the register 2, 11 specifies the register 3, 100 specifies the register 4, 101 specifies the register 5, 110 specifies the register 6, 111 specifies the register 7. So here I specify the ALU operations encoding. So 5 bit 0 specifies the just transfer A, 1 bit last one specifies the increment A, 10 specifies the add operation, 101 specifies the subtract operation, 110 specifies the decrement operation, 1000 specifies the A and add A and B, 1010 specifies the OR operation, 1100 specifies the XOR operation, 1110 specifies the complement operation, and 1000 0000 specifies the right shift operation, 11000 specifies the left shift operations. So here I give the examples of micro operations for the subtract R2 minus R3. So the input are R2 R3, the operation is subtraction and the result will be stored in the R1. So selection A have the R2, selection B have the R3. So those binary code will be 010 for R2, 011 for R3 and the destination is R1. So the binary code for R1 is 001 and the last operation is subtraction. So binary code for the subtraction operation is 000101. So next we have to see stack organization. What is stack? So already we know what is stack. Stack means last in first out. Which item we have to insert, that we have to insert first that item we have taken from the last. So for example we have to specify the submission of notebooks. So which one submit the note first, that person will taken the note last. So which is a good example of stack organization, which is also a storage device that stores information in such a manner that the item stored last is the first item retrieved. The stack in digital computers is essentially a memory unit with an address register that can count only. The register that holds the address for the stack is called a stack pointer because its values always point at the top item in the stack. So in stack organization, stack pointer is very, very important. So the stack pointer is nothing but which holds the address for the top value of the stack. So top value of the stack address will be stored in the stack pointer. So in stack we have performed two operations. One is push, another one is pop. So push is nothing but we have to insert the item is called as push. If we have deleted the item, which is called as pop. So these operations can be done by increment or decrementing the stack pointer register. So here stack organizations we have to see in the two categories. One is register stack, another one is memory stack. First we have to see register stack. So register stack or seeing in that way. So the incremental model we have to design the address 0 to 63, 0, 1, 2, 3, 4, 63. So here we have to push 3 elements, insert into 3 elements A, B, C. So C is the topmost elements. Those address will be stored in the stack pointer SP. So here we have used two flip-flop 1-bit register. Flip-flop is nothing but 1-bit register. So two flip-flop are used in this example. First one is full, next one is empty. Full, empty. So full is used for to check whether the stack is full or not. So empty register is used to check whether the stack is empty or not. So and also here we use DR register. DR means data register. DR means data register, which is used to take the data from stack and also insert the data into the stack. So here we use 64 word stack. So the stack pointer, that means address of the top of the item, contains 6 bits, because any address we have to store in the registers or any memory, we have converted into 2 power format. So 64 word which will be converted into 2 power format means 2 power 6. So the address is 6 bit. So the 1-bit register full is set to 1 when the stack is full. The 1-bit register empty is set to 1 when the stack is empty. So DR is the data register that holds the binary data to be written into on readout of the stack. Initially SP is decided to 0, empty is set to 1 and full is set to 0. So push operations are done here. So first if you want to add the item into the stack means first you have to increment the stack pointer. So first option we have to increment the stack pointer. So SP plus 1. Next we have to take the item from data register and it will be stored in the new location memory of SP. So next we have to check if SP is equal to 0 means then full tends to 1. So check its stack is full. So empty tends to 0. So mask the stack not. That means stack is full. So we can't insert any more item into the stack. So next we have to see pop. So which is pop operation. So taken the data from the stack pointer, memory of the stack pointer, and it is it is placed into data register. Then we decrement the stack pointer. Now we have to see if SP is equal to 0 means empty 1. So check its stack is empty. If it is full tends to also 0. So mark that means mark the stack not full. So here in today we have discussed about the general register organization. First we have to see CPU, what is CPU and what are the components available in CPU. And next we have to discuss with general register organization, how the registers are connected each and every other, and how the operations are performed, manipulations are performed. Then we have to see about register stack organization. So what is stack and what are the operations will be performed in the stack. At the last we have to see register set. Thank you to all.